Hello, hello, hello. Can you guys hear me? Yeah, good. Okay, so I'm Martin Casado. I'm the CTO of networking for VMware. And I'm going to be giving a talk on networking now that we have it and we're starting to get experience, kind of like what things look going forward. And I want to preface the talk with just a quick discussion on disruptive technologies in general. And I'm going to use servers as an example of this. So it's very difficult to sell disruptive technologies, actually, because there's almost always an education gap with the customer. And this is one of the reasons why, for example, open source very rarely ever does anything disruptive or innovative. So most open source will follow a mature market, right? So like if you do like Linux followed Unix, or MySQL followed Oracle, or Android followed, iPhone or whatever. I mean, normally, in order to sell disruptive technologies, you need to build out a sales force and you need to do like a high-touch, very technical sale where there's this educational component. This is just something to do with go-to-market. And the same thing happened with server virtualization. So normally, because that requires so much education, and because it's such a technical sale, you normally start with something very simple to articulate. So for server virtualization, compute virtualization like VMware, the initial value proposition was actually kind of weenie. It was server consolidation, which is very simple to articulate. You're like, okay, Mr. Customer, instead of buying 2 servers, buy 1 server and run 2 instances of this application, you save money, ROI, write a check. Right? This is typical how you sell disruptive technologies. And then normally what happens is once these things get in place and the customers are educated, then you can use the insertion platform to kind of change the laws of physics or change the paradigm because you already have education, you've got installed customer base, you've got support in the accounts and so forth. And so with VMware, originally very simple sales proposition, it got installed and then now tens of billions of dollars of value later, we've got cloud and vMotion and all this other stuff, which honestly, originally if you went in, you would have blown the customer's mind. It would be too difficult for users to consume this. And so listen, I'm a technical guy. Having built 2 startups now, like I've seen this as far as like technology meeting the customer place, but it's kind of a very interesting thing to understand. And so for the purpose of this talk, what I would like to do is talk about, okay, so network virtualization for the last 5 years has kind of been science fiction, and then we've had a few proof points, and then now we have some development, and now we actually have customers that have put it in, and it's kind of captured the imagination. So I'd kind of like to follow that curve a little bit to give you guys an idea of just provide some background, and then where it's being pushed that even we hadn't really thought of. And so that's how I broke down my talk. I just thought it'd be kind of a very simple narrative. So I'll provide some background. For many of you, this will be stuff you already know. Just please indulge me. It's not that I'm trying to be overly simplistic here. I just want to set a common language so that I can talk about some of the more sophisticated stuff later on. So the front half is going to be kind of setting the context, and then I want to talk about, okay, now that we're here, what can we do that is quite different? So I'm going to start the talk by giving a video. It's a little bit of a lazy thing for a presenter to do, but I think it does a good job of providing background on network virtualization. If you've been to the website, you've already seen it, but for those that haven't seen it, I think it's worth watching. And it's this kind of very high level, very fluffy, very kind of marketing-laden way of describing it. Then I will describe it after that, and then we'll get into more of the technical stuff. Good? Finally, this is largely your talk. I mean, I know all of this material. I've given this talk many times, and I love taking questions while I talk. So if you guys have any questions and I'm much more comfortable in the weeds. I'm way more comfortable at technical depth. So if you guys have any questions while I'm talking, please ask. I'll repeat it, and we'll go through it. And if they become somewhat disruptive, then we'll put it towards the end. But I don't want to lose any of you while I'm going through this. Good? Okay. So let's do the video.
Hi, I'm Raj. I work in IT for a company where innovation can't come fast enough. Last week, our CEO asks us point blank why it takes us so long to deliver services. Adam, our network engineer, starts explaining how provisioning network services is complicated stuff.
You know what? This is totally out of the audio is out of sync with the video. You know what, let me just skip the video instead of torturing you with it. I'm going to go ahead and talk through it. I mean, it's cutesy artsy, but it doesn't say anything that I won't say, so you guys aren't missing anything other than something you can look for on the website anyway. So let me just step through it. Okay, so how many of you saw the keynote on the first day in which I was? Okay, so good. So many of you have already seen this. I'm going to describe it in a little bit more terms than I did before, but it's roughly the same thing. So when we started Nicira, one thing that we noticed is that if you look at a new data center, it looks very, very different than traditional enterprise. And what I mean by a new data center, one where whoever built the data center controls the application. So take, for example, things like Google or Yahoo or Facebook or Amazon or Azure. In all of these cases, whoever built the data center controls the application. Oftentimes, they control the platform as well, like the operating system that it's running on. And if you take a vertical slice of those data centers, what's interesting is things that have traditionally been in the network, things like security, isolation for fault tolerance, segmentation, billing, et cetera, are actually re-implemented in software at the edge, normally as part of the application, right? And it really makes sense to do it this way, right? It really makes sense if I control my application to implement security, for example, in the application because I have much better semantics, right? I'm much closer, I know much more things, right? It also makes sense in, listen, if I'm Google and I've got all of these great developers anyways, why wouldn't I take value into my own hands and apply these developers to the problem? Another value is because now things are software objects at the edge, you've got all of these operational benefits, right? And finally, I'm actually decoupling features from hardware, which is a horizontalization, which means like now refreshing of hardware doesn't have to happen on feature timescales. Not only that, if I want to innovate new features, I can do it in software rather than waiting for ASIC design times, which are normally about 4 years. So when we first started in Nicira, which was, whatever, seven years ago now, we were working with a couple of these really big data centers. And one of the biggest aha moments that I had at the time was this wasn't limited to 1 or 2 big data centers at all. There was hundreds of these guys. Anybody that was kind of building a new data center where they owned the application was building it this way. And if I could characterize what they looked like, if I could just do an average of what they looked like, you would have a very simple physical network. It was generally L3 ECMP, nothing else. No ACLs, no L2, just L3 ECMP. Then you'd have your servers. Your servers would run whatever, sometimes virtualized, sometimes not. They'd run your application. The applications would do a lot of these high-level things, discovery, billing, segmentation, and then often you would have some L4 through 7 services, like a load balancer. So at that level, at that very, very high level, the world is now a very simple switching fabric, and then there's compute. And then everything else that we normally think of in the network is part of that software compute layer. So, and I'll talk about this a little bit more later. So one of the premises of Nicira, which is that's great, that's something that you can do if you own the application or the platform, and you have lots of developers. So never mind, this is not about being large or being Google. This is about, I am some random Web 2.0 company that I'm building my own data center, and I have the developers that are making my application. That's no problem. And when you do the cost economics of that, they're fantastic, right? Things are in software, the development is very quick. But the problem is if you look at that towards the enterprise, most enterprise don't control the application or only control a subset of the application, and they don't control the platform, right? They don't write the operating system or they don't write whatever. And so, you're comparing these side by side. This one from a CapEx, OpEx innovation model is way better on the new ones, but if you look at the IT model, the traditional enterprise model, they seem kind of stuck. And so the question that we asked, which is like, would it be possible to look at the kind of Web 2.0 model and apply that to the traditional IT in a way that you don't have to modify the applications, you don't have to modify the platform or control the platform, but you get all of the benefits. I mean, that was kind of the mental exercise that led to Nicira originally, if that makes sense. Right? And we kind of knew that this was real when we looked at a number of these Web 2.0 guys, and they were awesome at building their web service, right? They were awesome at building their search engine or their EC2 cloud or whatever, but if you looked at their internal IT, it still blew, it still sucked, right? And so, for example, one of our largest customers, they're one of the most innovative Web 2.0 companies. If you look at their web service, they've got a very simple L3 fabric, no L2 at all. Most of the functionalities in the software at the edge, But if you look at their internal IT, it's a museum of computer science past, right? It's everything, provisioning times are a long time. In order to get a new development environment, it's days or so forth. And it's not that this company doesn't have the wherewithal to provision servers or develop stuff. It's just it's a much harder problem with IT than it is if I'm building my new data center. Okay, so that is the premise by which all of this happens. So now let me kind of create a quick ontology of what a data center looks like in the NSX world, some of the trends we take advantage of, and the value it provides. Okay, so data center. So for the purposes of discussion, a data center has a physical network. For the purposes of NSX, which is the product I'll be talking about, it doesn't matter what that is. So as long as it provides point-to-point IP connectivity, we're good. So we have, we've worked with customers that have L3 ECMP fabrics, lots of Cisco fabric path. We have Trill, InfiniBand. To us, it's all the same, right? The one thing that I would hope in a physical networking fabric is that it doesn't have major bottlenecks, right? Like there's no way that from software on the edge I can overcome something like a vastly oversubscribed networking fabric. But you have the physical network fabric, it can be anything, we'll never touch it. You string it up however you want. Connected to that, you have your servers. Again, this is x86. And in a virtualized data center, you're going to run a hypervisor with a vSwitch within it. So whether, in our case, the background of this here is like working with like a lot of the Linux-based hypervisors, Zen KVM, of course now in VMware, ESX. So for the purposes of this conversation, you assume that there's a vSwitch, you assume there's a hypervisor, and I'll talk later about direct physical integration. So all of the software installation happens at the edge, and then those together, we create NSX. So if you think about, like, the simplest way to think about NSX is, okay, so let's say I have my data center, it's brownfield, it already exists, I'm running ESX, whatever. I talk to Martin, he sells me NSX, what do I install? You're effectively upgrading the vSwitches to something that's a little bit more sophisticated. And then there's a controller unit, or a set of controller units that manage all of those vSwitches and harnesses them together, and then just uses the physical networking fabric as a backplane. And for those of you, how many people in the audience are networking? Awesome. So if you guys know about like traditional network chassis design, the best way to think about it is the difference between a line card and the backplane. So like a traditional networking chassis, you've got this box where you put line cards in, and then you've got a backplane. The backplane effectively provides connectivity between the line cards, and the line cards themselves are what has the intelligence and provides the services, right? And the data center design, whether you're looking at Google or you're looking at something like NSX, is effectively the same thing. You've got this physical network, it's providing connectivity on the backplane, and then you've got all of the software on the edge that's providing the intelligence. So all of these harnessed together now, you use this to create a network hypervisor, which is a cutesy name, which means almost nothing. But the point is that you use this to recreate networking. And so we want to create virtual networks. So it's reasonable at this point to ask, like, why are you recreating networking? Why are you having L2 and L3? Because when you recreate networking, you want it to look exactly like it did before. And the reason is because if you're changing the abstractions, if you lose L3 or you lose IP naming or you lose ACLs, like pretty much nothing that has existed before as far as tool chains or people's brains or applications can use it, right? This whole exercise from the beginning, the entire exercise is how do I take existing organizations, existing applications, and then move it to a fully software model, which means it's my responsibility, it's our responsibility to reproduce networking fully. So if you create a virtual network, it looks exactly like a physical network. It should look exactly like a physical network, right? You should have L2 connectivity. You should have complex topologies. You should have L4 through 7 services. You should have all of the RX, TX counters, and SNMP, and NetFlow, and SFlow, and spanning, and whatever you need to accomplish what you do today in your operations. And so the hope is you install this at the edge, you turn it on, and now instead of you managing boxes and wires, you're managing this software entity that looks like something real, but your tools still work against it. You still know how to think about it. Your teams know how to think about it. And then now you can use this in a way that kind of follows more of a VM model. That's the goal. if that makes sense. And also at this point, I think it's also good to point out, I think a lot of times people get really confused at the difference between automation and virtualization. So let me just address this up front, right? So if I could put this up here, and like one totally reasonable question from you guys would be like, listen, what if I have a bunch of scripts and I automate provisioning on a physical network? Does that approximate what you're doing here? Let's say that I get a bunch of Arista, I deploy it, and I write a bunch of scripts, and then like when I need an L2 environment, I set up an L2 environment. When I need an L3 environment, I set up a VRF. That would be automation. Okay, so the difference between automation and virtualization is automation, you automate what exists. You buy N pieces of gear. That gear is capable of a certain number of things. L2, maybe L3, whatever it is, and then you automate that existing gear. So you can't make it do something that it's not able to do otherwise because you're automating it, right? Virtualization is I'm introducing this platonic world, this new universe that is totally independent from the underlying hardware, so I can make it do things that it wasn't originally able to do. For example, very common use case for us is you have an IPv4 L3 backplane. The switches don't even have to support L2. I can give you L2 and I can give you IPv6. Right? There's no way you could automate that in the physical infrastructure because let's just say it doesn't support IPv6 or it doesn't support it well or it doesn't have a good L2 stack. So the idea is I'm actually providing networking functionality at a new layer all in software, and I'm using the physical network as an interconnection fabric. That's not automation. And I just want to say that up front because I think there's a lot of confusion around that point. Okay, so the whole goal here is, okay, I want to change operations, and so instead of giving somebody a physical device that you have to deal with wires and atoms and this and that, I'm going to give you a virtual abstraction, and now that becomes the focal point of operations or programming. Software abstractions are awesome for a number of reasons, which I'll talk about later, but just to kind of hammer home a point, they need to be complete, right? So for example, if you get NSX today, then you get L2, basic L2, right? So if you set the multicast bit, it'll broadcast. You get L3. So hopefully, for example, L2 doesn't scale whether it's physical or virtual, right? L2, by definition, the service model of L2 is broadcast, and by definition, that doesn't scale. So if you want to run a really large workload, you probably shouldn't use L2 in any respect, right? So L3, and then of course you've got, I think this is load balancing, firewalling, VPN gateway, etc. So from what, I mean, the way you can think about it is like, okay, I've got like this erector set. I'm not sure, is erector set like like a totally American thing? So you've got this set of primitives where you can create nodes and links, and you can wire together arbitrary topologies with arbitrary addressing space, with arbitrary protocols, and you can make an arbitrary number of those, right? So for example, L3 fabric, I mean, we have customers that run tens of thousands of these in hosting environments. So you'll have a bunch of L2 environments, some big L3 environments, some that require L4 through 7 services, whatever. All multiplexed on the same physical hardware. Make sense? Okay. As far as, if we go back to like the original problem statement is, I want to be as non-disruptive as possible to add some marginal gain, and if that required you to change your existing services, that would be totally disruptive. Like people love their F5s, and people love their Palo Alto firewalls, and people love a lot of their physical appliances, and that's great, right? And so as part of this exercise is wanting to be as non-disruptive as possible is like, I'm going to give you this erector set, or this set of primitives that you kind of mix and match, but you should be able to also plug into your existing middle boxes or whatever. Right? So that's a piece of it. So for example, if you want to create a virtual network and attach it to an F5, be my guest. Right? And so we need to support a model where things that exist today can play in this new realm, right? The point is not to recreate all functionality, but to make composable pieces that you can then automate. And we're finally at a point where like there's actually broad enough adoption that we can talk sensibly about it. I mean, in general, I don't know, I mean, how many of you have been following kind of like the SDN wars and then kind of all the discussion around it? A fair number? So, I mean, there's been all of this discussion in SDN, and this is kind of a term that was made up in 2009 that meant something specific, and now nobody knows what it really means, like least of all me. But like, before you have product, you can't compare products, so you always have these stupid architectural discussions. And I think everybody's confused as a result of that, right? Where instead of actually saying, okay, I've got my product and you have your product and we'll compare feature sets and performance, we say, well, I'm using BGP and I'm using MPLS and I'm using blah, blah, blah. And like you have these wars that end up being like arguing from your gut, which is normally actually carried out by marketing people, which just confuses everybody. And we're coming out of the tail end of that. Like so, people are so confused about OpenFlow versus network virtualization versus what we do versus what Nuage does and blah, blah, blah. And you know why? It's because nobody's had product and there's been very few production deployments, so we're all just talking. And what's nice is in the last year, there's been a lot of production deployments at scale so we can actually talk about things. Like what is hard? Why do people buy it? What is the value proposition? What are the scaling properties? Independent, even if you have the best architecture in the world, if your software developers suck, your product's gonna suck. Right? I mean, how many people here are virtualization guys? Good. So do you guys remember like the debates between dynamic translation and paravirtualization in like the late 90s? Like this broke up marriages, right? Like, oh, paravirtualization is better because we can do page table batching and therefore we get better optimization with interrupt coalescing. And the dynamic translation guy is like, no, like we'll never like modify the guest, and like that's the wrong approach. And like there was all of this discussion, but that was before anybody had real products and the products sucked, right? And now nobody talks about that anymore because it doesn't matter. Really, at the end of the day, you should be able to look at a product and know if there's customer value. Clearly, instead of having to like have these stupid arguments about, you know, what's better. So I actually want to talk kind of from a position of like what customers are deploying and what they're using rather than kind of making appeals to your architectural intuition, because I find that to be pretty flawed anyways. And the least obvious thing to me is why people take the risk on a new technology, pay money for it, you know, attach their career to it, and put it in production. I mean, we've got a lot of production deployments today, and consuming any new technology is a huge risk. So there's a reasonable question, why do people do this? And I mean, originally, we were really naive. We're like, people are gonna do it for cost savings or for operational efficiency, and all of these arguments are too difficult to make. They're all very fuzzy, right? Like, maybe there are operational savings, but education is really hard and people hate you, right? So it's very difficult to make that. Or, you know, maybe there's some capital cost savings, but like there's a risk on new technology and you're not gonna be replacing switches. It turns out for almost every early adopter, the reason that they're buying this stuff is just to reduce the time to do something. The case of eBay. eBay builds an online marketplace, but like when it comes to provisioning a dev environment, it took a long time because network provisioning is hard. Right? So to reduce that, reduce the time to like for a developer to sit down and to get a dev environment from whatever it is, 49 days to 30 seconds, that's value, right? It's value that you can articulate internally. Same thing for our hosting providers. We work with a number of telcos. They host customers. From when a customer signs a business agreement to actually has an environment in the cloud, reducing that from months to days, okay, so you get to money quicker. That's pretty easy to make. So remember before I said server virtualization had its very simple value proposition, which was server consolidation. So in my opinion, the very simple value proposition for network virtualization is just reducing the time to do network provisioning configuration. It's a total undersell. It can do an awful lot more stuff, which I'm going to talk about, but that's what makes people adopt and write checks today. And I think it has to. It's just part of like a sales cycle. Early sales cycles are really hard. So if I look at kind of where we are in the adoption cycle now, I mean, so we started this year in 2007. All the OpenFlow SDN work that I did was in between like 2005 and 2007. So like I've kind of seen this kind of bump along the entire way. And like it's only in the last 2 years where we're seeing a lot of adoption. And I think that's a result of a number of things. People are comfortable with the technology, the products are better, but honestly, most importantly, everybody's pouring marketing dollars into this. So like, whenever you're in an area and you look around you and like big companies are like throwing tens of millions of dollars in marketing dollars into an area, it's great because everybody gets educated, right? So if Cisco's marketing this and Alcatel-Lucent's marketing this and Juniper's marketing this and whatever, which is happening now, the entire customer base gets educated. So early on, nobody thought you could do it. I got laughed out of many places. 2011, I think people agreed that it's actually plausible. They didn't know why anybody would take the risk. 2012, we had a number of engagements and everybody was just waiting to see if they would blow up. 2013 was kind of engaging the VMware broader customer base, and now we've got a number of engagements that are either in production or going into production. And so we're kind of understanding that. And by the way, if you were to ask me what is the #1 hurdle to adopting this stuff, organizational, full stop. Which is like you can have a customer, they've got money, a use case, they love the technology, and the entire deployment can totally fail because you get in, you start to operationalize, and it's like the networking guy versus the security guy versus the virtual admin, and even if you figure out all of that turf wars, then you've got what communication has to happen for support. I mean, the organizational issues are very difficult to deal with. Fortunately, most of them have to already have been dealt with if you're dealing with cloud. Cloud requires you to kind of change things anyways, and so most of the engagements we do are like someone standing up a cloud and we stand behind it. Okay, so my last slide before I'm going to go into kind of more of a technical view on moving things forward is you guys have probably all seen this slide now, but I do want to talk about it. The reason that in Nicira when we created it, we looked at, like I said, the big data centers, and we're like, okay, this is clearly a trend. At this point, there's kind of no arguing that the right way to build a data center as far as OpEx and CapEx is the way that these big guys do, because they've done it and they're awesome, right? And if anybody went to Google and said, your data center doesn't perform because you don't do X, in special purpose hardware, they would laugh at you, right, and close the door, right? These are the most successful data centers on the planet, and at a high level, they're just switching fabrics and just x86. And they probably account for 20 to 30% of the world's workloads. Right? If you look across all of these guys that build it this way. Most successful operations, Darwin has already spoken, this is the right way from an architectural level to build these things, if you can get it right. Does anybody disagree? It's a strong statement. No? So Darwin has kind of spoken architecturally, and if you can take a vertical slice of one of these data centers and you compare it against a traditional way of doing it, it's just better in pretty much every way. The insertion point, which you guys know, is in the vSwitch. And the only way that this is practical is because there are now way more virtual ports than physical ports. Way more. And it's pretty obvious. There's more virtual machines than there are physical machines now. Virtual machines, by best practices, normally have 3 vNICs. There's a consolidation ratio of what? On average, 20 to 40 VMs per server. So I'm already 120 to 1 virtual ports to physical ports, just using simple back-of-the-envelope math. And these virtual ports are already touching every one of your packets in software. It's not like network virtualization changes anything so I live mostly in the world of circles and squares, and I live at a very high level. But at that very high level, there's nothing changing in the architecture between something like network virtualization and existing virtualization and something like a Google data center at a very high level. And we can drill down at any depth that you want, but at a very high level, they all look the same. Okay? Okay. All right, so you guys have a basic idea of why we started Nicira, which is we looked at 2 trends. The trend was wow, it looks like Darwin has already chosen a model for the data center. And most ports are virtual, and they're running on x86 already. And so if you look at those 2 trends, you align and say, wow, this is an opportunity to do something disruptive. Because those virtual ports are below the application, we can add networking functionality there and not change the application. That was the whole premise of Nicira. We built NSX. NSX allows you to try and get the benefits of these big guys without changing your application or owning the application of the platform. And now we're at a point where people are deploying it. The primary use case is provisioning time. The primary use case is provisioning time. So, but the biggest hurdle is organizational challenges. So that's kind of been the first part. So now let me talk about, but once you put it in, what can you do that isn't kind of part of this fairly basic routine stuff? Any questions so far? By the way, is this making sense? Yeah? Yes? Okay, good. About 25% of you said it was making sense. All right. Okay, so let me just do conceptually an interlude. So when you virtualize things, you gain a lot of power. It's like the proverbial level of indirection in computer science, right? So virtualization has always been like your way of standing outside of something and then being able to fiddle with it. right? Compute virtualization, you put something in a VM, and then you have an awful lot of power that you can use to do things like vMotion. It's an incredibly powerful concept fundamentally in base computer science. And I just want to talk about why that is. And I want to go through 4 things. So the first one is really obvious, but it's really important. It's like, once something's in software, you can actually wrap an API around it. I know this sounds really obvious, but it's actually not. And I think people miss this point. So like, a physical server, you can have an API to like modify the BIOS and maybe install OSs and fiddle with applications, but you can't put an API to like plug in a wire, right? I mean, because the world doesn't have a programmatic environment yet, right? So like when you're dealing with atoms, you can't actually move things around and plug things in and out. I know this sounds really obvious, but people really miss this point because they'll look at virtualization, they'll say, well, why can't I do this with a server? Well, because it's physical atoms and you can't program that, right? But once you virtualize something, you have this software entity and I can make this an object in a program, and that's why you get the operational benefits of VMware, $40 billion market cap company, because now I can create these things, I can plug them in, configure them, whatever I want, standing from outside of it. And by the way, this always sounded very obvious to me too, until spending a lot of time with it. It's actually a very powerful concept. The second one is, it's awesome to have all of the state of something, right? So a lot of the times, like if you look at compute virtualization, it's had, like operating systems have had virtualization forever. Virtual memory, right? Processes, virtual file systems, but there was never a place that you can be like, I want like this entire thing and I own it up to like the page tables and I can like snapshot it and copy it and move it around, right? You can never treat it like a file, but like treating things like files is awesome because it's a primitive for managing things. For example, I want to snapshot the full state of a VM. I want to move it, I want to clone it. So you can do the same types of things, of course, for virtual networks if you own all of the state. And whenever you virtualize things, normally the next step is, now I've got a handle to this, to manipulate it, I also have a handle to all of the state that I can use to do interesting things. The next one is introspection. So if this is going to sound obvious again, but if I'm something, I can't really introspect because I am me. I mean, I can kind of have some reflection, but that's very different than like, you know, standing outside of something and looking in. Right? This is very commonly used by operating systems to do cool shit. Like for example, page table sharing, right? So this is like, if you have a whole bunch of VMs, you can look into them and say like, wow, there's all of these 0 pages, so I'm gonna alias them all. I'm gonna talk about compute virtualization. I'm gonna alias them all to one 0 page, right? So I can look inside them, I can see inside them, I can see across multiple of them, and I can do interesting things across the broad set. Does that make sense? This is something that's heavily employed paradigm in virtualization that adds a lot of kind of net new that you couldn't do. Like a single operating system can't really do that because it's not outside of itself or outside of multiple instances of itself. Very similarly, if I control the environment that something lives in, I can manipulate the laws of physics, right? So I can actually change where it thinks it is. And so it's similar, but it's not an introspection thing. It's like I can change where it thinks it lives and what it's doing. And this is used all of the time in compute virtualization. For example, making it feel like time is going backwards. I mean, there's all sorts of stuff that you do if you stand outside of it to manipulate the environment. And in network virtualization, this becomes actually very interesting. Because for example, in network virtualization, I can move things all around and then manipulate the environment so it doesn't think it's moved, so like the IP addresses stay the same, for example. Very common use case. Without having like clear abstractions like virtualization, you could do it with things like lists, but you're piecing together primitives. You don't have like a unified abstraction to deal with it. So any questions on that? Okay. So let me talk about now, so you have network virtualization. Virtualization is a very powerful, fundamental paradigm that you can apply to things. What can we do that's interesting? Let me first talk about visibility and debugging, just because it seems to be a common topic and a topic of interest. So the first one, when it comes to kind of visibility and debugging in a virtualized data center, it's already a mess. Right? Virtualization, compute virtualization kind of broke it because if VMA can't talk to VMB, you still have to figure out where they live. You've already decoupled the OS abstraction. You've already decoupled the VM from the physical machine. And so, VMA can't talk to VMB. I mean, something will tell you where it lives, but something is mapping from these two abstractions down to the physical machine, right? And so if you do something like network virtualization, it has to maintain, because it's maintaining these layers, it has to maintain all the information that you need to map between the virtual world and the physical world, because that's how you do virtualization. Virtualization is always some array that, so whether it's compute virtualization, whether it's memory virtualization, or whether it's file system virtualization, virtualization is always the same. It's one array, and that one array maps virtual address space to physical address space. Now, that array may be distributed all over sorts of places, but that's the heart of all virtualization. And if you maintain that page table, or whatever you want to call it, you have all the information you need to map from the high level down to the low level. So I'm going to actually step through this really quickly. Actually, first, let me step down let me step back really quickly, and then I'll get to that. So the basic idea of debugging and visibility in a virtual network is, today, we use a whole bunch of primitives to try and approximate virtual networking. Things like ACLs and VLANs and VRFs and MPLS and whatever we can, right? And that's kind of littered throughout the network, and that's fairly complex. So the idea for virtual networking is, instead of having one very, very complex environment where VMs can be anywhere, and I've got all of this stuff littered in the middle of the physical network, I'm going to create N networks, the physical network, which has become much simpler, and N abstractions, each one of these that you can monitor by itself. Right? So instead of having, today, instead of having this fairly complex network with stuff in it, I'm saying, okay, if VMA can't talk to VMB, look at the virtual network that it's connected to. That has all of the counters. Your tools work against it. It'll tell you if a packet's being dropped. And if there's no problem there, we'll tell you where in the physical network that is connected, and then you use your existing tools on the physical network. Make sense? So instead of having now you actually have these high-level abstractions that your tools know how to do, and we have the information to map between the two of them. Rather than bore you with like a specific example of that, I'm just going to go ahead and stop through. So this is a specific example of how you do it. Okay. Okay. But that's just kind of bringing it back to the status quo. It turns out that once you have all of this stuff in software and you have all of the counters, you can actually do things today that are well beyond what you actually can do in a traditional data center, virtualized data center. So how many people here are familiar with VCOps? Okay, cool. A lot of you. So VCOps. VCOps is a cool tool for doing management. I didn't know anything about it before starting to work with it, so I'm fairly new to it, but it's basically, we'll track a whole bunch of things. It'll do dynamic threshold detection. So if for example, it's monitoring a field, and that field becomes abnormal, it'll tell you about it, and it's very good at managing a whole lot of data and doing all the trending analysis. That's what it is. So we're working on VCOps integration. Here's an example from our internal cloud. So we, of course, use network virtualization. We have our own cloud. We've got well over 10,000 virtual ports on it. And on the left, this is a dashboard from our internal cloud. And if you look at it, that's kind of like the state of all the virtual networks. So from my experience working with a lot of these large hosting providers, like whoever it is, Rackspace or AT&T or whoever, like the way to tell if something's broken is the phone calls, right? Because these things are so complex that unless somebody's actually experiencing a problem, you probably don't know that there's an issue. And this is no fault of anybody's, it's just you don't have enough state or enough handle to do this. So the idea here is, at a high level, I should be able to know for every virtual network, which can have anywhere between, for every one of those dots was between 2 and 100 VMs, say. If the dot is green, we're tracking something like 26 different metrics. All of them are good. If the dot is red, that means that there's a connectivity problem. And if the dot is yellow, then we've crossed some threshold. Maybe latency is high. Maybe we're seeing packet drops or something else like that. Right, so again, because we own the entire edge and we have all of these state and we have all these virtualized abstractions, I can actually now display from a global standpoint the entire state of the network, and I can monitor it. And by the way, the network virtualization, to build the product, you have to do all this stuff anyways. Like, network virtualization doesn't work unless you maintain this much state. It's endemic to the system. I have to maintain this page table, and I have to monitor these things. And so the only reason you wouldn't get this is because I decided not to expose it, not because the system can't do it. I mean, you have to have this stuff if you're building this product. You have to maintain this amount of stuff. So on the left is the full dashboard. On the right, that's the virtual topology, the VMs. And below are a bunch of stuff that we're tracking, RX, TX, whatever. So this is a virtual view. You can also have a physical view. So this is, again, because from we're in the edge, we can actually monitor the physical network. So that thing on the bottom is a heat map of the physical fabric. Again, the way that something like NSX, pretty much all network virtualization is implemented is you build tunnel meshes. So we're monitoring the entire physical fabric anyway, so I can tell you if there are hot spots between any 2 points. I have to. I mean, I'm building a tunnel mesh. I actually have this. And I have global visibility. And because like I said before, I'm maintaining this page table. I'm maintaining this virtual to physical mapping. I can tell you exactly who's affected by anything. So if VMA can't talk to VMB, I can tell you exactly where they are. And now we're working on the ability to tell you what path the flows are taking. And I can map it down to physical components. If you look at any physical components, like I wake up in the morning and I kick a router and it dies, I can tell you exactly which virtual components are mapped to it. Does that make sense? So you should be able to go from physical to virtual and from virtual to physical, provide a global view of the entire operation. And what's nice is because all of this information, instead of using these kind of steaming piles of 1980s technology like SNMP, which are like really baroque, I mean, this is all kind of modern API based. Like big data analytics are very easy to apply to this, right? Getting like big data feeds. It's very, very difficult with these old protocols where you like lose traps to actually build an analysis engine. Very difficult. Very quick on snapshot cloning and modeling. So like I mentioned before, like when you can treat things like a file, it's awesome. So it turns out that we can like reproduce any environment. Let me just kind of, so we can reproduce any environment. So practically how this works in the field. So if we have a customer today and a customer is a really large customer and normally they have a bunch of physical gear and they've got a bunch of weird configuration, I can actually go and I can snapshot the entire state. I can reproduce it locally and I can test that. And where this is often seen in the field, and actually we hadn't thought about this originally, which is a lot of customer environments they'll have dev, staging, and production, right? And so they'll do stuff in dev, and then they have to move it over to staging and move it over to production. And then moving all the networking configuration and all the ACLs and stuff in some operations can take months. And the reason is because there's a lot of boxes and the environments are a little bit different. Like very rarely is the dev environment as large as the production environment. I mean, that would be a serious capital investment. If you have all of the state like a file for the virtual network, there's no reason I can literally the entire thing, tens of thousands of virtual networks or hundreds of virtual networks, pick them up, move them to staging, pick them up, and move them to production. Like there's nothing you're missing except for the ephemeral state for like TCP at the end, which we don't really care about because, I mean, you're moving VMs, right? But all of the configuration, all of the topology, everything you can actually move between different environments. And the way that we use these with customers is for very complex customer environments, we actually test upgrades locally. So we're like, we'll snapshot the environment, we'll bring it locally, we'll actually run the upgrade against it to make sure it works, and then we actually do the upgrade on the customer prem. So another cool thing, so virtualization in general has got this awesome thing that it decouples correctness from performance. And this is just the power of computer science and abstraction. So good abstractions will decouple things like correctness, visibility from the implementation, right? So your decoupling mechanism from how something works. So if I give you a virtual network abstraction, here's your virtual network abstraction, you have something running to it, like anything I do below to fiddle with it, to improve it, or to optimize it shouldn't affect anything that you do. So today in networks, we don't have good decoupling of correctness and mechanism a lot of the time. So for example, adding an extra load balance or even extra paths normally requires reconfiguration and is often visible to the apps. Things like extra paths or extra IP addresses. But in this case, I should be able to just give you a virtual networking abstraction and then you can add capacity below or I can improve my implementation and it'll just become faster without affecting anything else. And I think the best example of this is distributing services. So let me give you an example. So when we first started this, ideally, if I give you a virtual network, everything is implemented in a distributed fashion, meaning a little piece of it is in every virtual switch, right? So if I give you a firewall, a little piece of the firewall is running in every virtual switch so that you don't have any choke points and you get full aggregate bandwidth of the fabric. You should have a terabit of bandwidth and a terabit of firewalling. But it doesn't always happen that way. So for example, when we first implemented routing, distributing it was too hard because we were on a timeline, so we actually ran it in a VM. Think about like running Viata in a VM. It's a horrible model, right? It's a horrible model because now you've got all of these VMs that are connected to like a gig or 10 gigs. Say you have 40 of them, and then like to send traffic north and south, you've got to send it through a VM, right? I mean, it's like you're going from 40 times 10 gig down to whatever, 2 gigs or something like that. So ideally what you want to do is you want to say, okay, instead of having everything go through a central VM, I'm going to go ahead and break that up and distribute throughout the edge. Much better model just from a standard computer science standpoint, clearly, right? So we've actually had a number of instances where we have services, L3 for example, where customers are using it. They were under a worse implementation for whatever reason, and then we improved it without changing anything. And I actually have a latency graph of one of these, which is, so this is for L3, this is a customer environment, a very large customer environment, where these are the latencies that were actually happening between north-south traffic. So you had VMs, they were talking to each other, they're talking to the world, they're going through a choke point, so think of like a Viata router in a VM type model. And then we did a software upgrade, which upgraded, for whatever it is, 5,000 virtual networks, and then the latency totally improves and nothing else changes. Make sense? So I only had one more example. I think I'm going to skip and just go to questions, but it's always cool when you do virtualization to do stuff recursively, just because it's cool. And often it just shows the completeness of your implementation and you have no good use case for it. But like getting ESX to run in ESX is really hard and it's really cool, because it shows you that like anything that you do can itself be done on itself, right? So you can do virtual networks within virtual networks within virtual networks if you wanted to, if your system can do it. And so it turns out that, and this actually took a while to get right, so you can do things like NSX recursively in NSX, which we actually used for all of the partnering programs. So to make a long story short, anytime someone develops on NSX, one of our partners, they're actually developing NSX within NSX recursively. Does that apply to you? Probably not, but it's cool. And this was actually used recently kind of at scale. Okay, so just a capstone. So the idea of this talk was actually to set context for those that haven't heard me talk, to provide background, to provide kind of where we are on the adoption cycle, to provide kind of some of the hurdles to adoption and the value proposition, and then to talk about kind of base concepts of why this stuff is cool and how it's being pushed forward. There's a lot of stuff I didn't talk about that's going on. Things like handling per flow, elephant flows, MPLS integration, all sorts of other stuff. So I don't want you to think this is an exhaustive list of stuff that we're doing, right? So it's supposed to be more of a fundamental foundational talk, but I'm happy now to answer any questions about pretty much anything I can right now. Good? If there are questions. Yeah?
What do you think would be the right strategy from the physical network vendors to participate on the SDN?
Yeah, so the question is what is the right strategy for physical network vendors to participate? And so for pretty much all virtual networking solutions that exist in the market today, the architecture looks roughly the same, which is you have an edge, sometimes the edge is the top of rack, sometimes it's the vSwitch, you have an overlay, and then you have a fabric. And sometimes that's hidden from the customer because it's buried inside a fabric, but that's kind of what it looks like. So for physical vendors to work with us, for example, there's a number of areas. Top of rack integration, so that the top of rack can participate in the overlay to allow physical workloads to participate is one. Another one is unified operations and management to help with debugging is another. And the one that I like, the kind of one that's coming up now is, it turns out in data centers, for the majority of all traffic, the best you can do is multipathing with ECMP. You can't do anything smart with the traffic because the traffic's too bursty. So if you try and do traffic engineering, for example, it's pointless because by the time you've made a decision, like the traffic pattern has changed. And this is provable, right? That's 99% of the flows. But for 1% of the flows or 5% of the flows, some small set of flows, they're actually elephant flows. They're much larger, and you can actually do something smart with them. So an area that we're working with a number of our hardware partners is to identify elephants versus mice, the small flows versus the large flows, is actually hard to do in an ASIC because you require a lot of SRAM. So we can actually identify those at the edge. We can identify an elephant. We can tell the physical fabric that they're elephants, and the physical fabric can actually optimize based on that. And so to first order the right partnership for the hardware guys, provide a good fabric, provide integration for the overlay, provide operations and management, and going forward, actually flow level control for the large flows, whether it's putting it in a separate queue or doing something smart, is a great integration point. Any other questions? Yeah? The requirements for the underlay? Yeah, okay, so so the questions are, what are the requirements for the underlay physical network? So the base requirement for us is just point-to-point unicast IP connectivity. However, there are a number of things the underlay can do to improve performance. For example, offloading multicast, packet replication is something you want to do in the physical network. Handling elephant flows, like I said. So it turns out if there's an end-to-end user performance problem, and it's actually the network's fault, which is actually very rarely, it's normally somebody else's fault, like the hypervisor, but it's actually the network's fault, it's almost always because you have a large flow trampling on a small flow. So doing things like if I identify an elephant, having the underlay map it to a queue is a great performance win. And then doing something smart with that is even better. And then of course all the operations and management. So independent of whether a company provides both the overlay and the underlay, or you have a standard interface between the two, these are pretty much the identified 5 touch points where you can add value. Does that make sense? So handling elephant flows in not a stupid way, packet replication, not being oversubscribed, having unified latency, just standard performance stuff, are all things that the underlay can provide. Yeah?
Do you have to implement the wall of NSX, or can you choose, for example, to implement distributed firewall without implementing routing, virtual routing?
Yeah. So I mean, NSX at like the core level is actually just a way of building arbitrary topologies with no service model. So on the core technology, you could build whatever you want. I mean, you could have like a firewall with no routing or no L2 if you wanted to. So these are all composable pieces. Now, like product packaging reasons may make that more difficult, but the core architecture is you have these nodes which don't even have a forwarding notion in them. And then it's the forwarding notion which will give you something like L2 and L3 and firewalling. But like, let's say like you woke up tomorrow and like, I have got this awesome way of handling packets. It's not L2, it's not L3, it's not even firewalling. It's my new algorithm, right? Like with NSX, you could, you create like this virtual network and you can implement your own, I mean, you'd have to be part of the partner program to do this, but you could implement your own forwarding algorithm to do that. So none of this is like, the L2 and L3 is not endemic to the system. It's just a forwarding paradigm that we've implemented. And you can mix and match and compose those as you'd like. And architecturally, again, like from a product standpoint, it's different, but architecturally, sure. And this is what like a lot of our partners do, is like whenever you extend a platform like NSX, you want to extend it one of 3 ways: data plane, control plane, and management plane. And that would be kind of a data plane type extension. Or you would just implement, you'd say, I just want your firewall and nothing else, which is fine.
Could you talk about the early adopters and sort of the day one problem of the management plane? It would seem like being able to map the overlay to the underlay is 100% critical here to know what's happening. What are the early adopters? What have they done? Yeah.
So, well, there's kind of 2 questions there. So, do you want the answer to what do they do about the overlay versus underlay? So it actually turns out that it's easier to manage, right? So today, if you have 2 VMs that can't talk, you still have to go through a notion of finding out where they are and where the traffic path is going. If you implement something like NSX, I already know that for you, so you don't have to figure that out, right? So if let's say you implement NSX, and you've got a performance issue between VMA and VMB. I can tell you whether there's an ACL that you've configured that is dropping it, or whether there's some problem in the physical network. And the reason I can do that is because I maintain all that state on the edge. So day 0, I'm actually improving your ability to debug. But all of the organizational problems I've talked about aren't technical. They're always like, the hurdles in debugging are the compute guys don't normally talk to the networking guys. It's organizational, it's not technical.
But if there were a physical problem,
Yeah.
you would just see the endpoints, not the physical problem.
So, well, there's two things. So I can tell you exactly which flow is being dropped from the edge and exactly where they are on the network, which would be exactly what you do today. So today, exactly, if two machines can't talk, exactly the information you get are these two machines can't talk, and I can tell you exactly that information. Not only that, I can tell you exactly which flows are being dropped, because if you're doing ECMP, they may be taking different paths. So I can probably tell you a lot more information than you have today. If you have an L3 fabric, I can actually tell you what link is being dropped, because I can do OAM myself. So we actually are working on a debugging thing where I actually do link level debugging. So like if you have latency issues, I can tell you what link is the problem. So I actually think like it's a net win. I think it actually things become much easier. Any other questions? No? Okay. Oh, question? Yeah, sure.
What is the critical size for a customer to do NSX? Because compute with server virtualization, even 10 to 20 VMs, it makes sense for a small customer. But NSX, is it for just large customers or?
This is actually a very interesting question. So that was originally what people thought, but because the value proposition is actually time to provisioning, it's not the size of the customer, it's whether they're actually trying to do things quickly. So we sell to small customers and large customers, and like the gating factor is whether they have a dynamic environment. We have many small customers who like are, whether they're small service providers or small development shops, where they want to remove IT hurdles. And that is by far like the best metric whether someone's interested in this. It's not their size. There's a lot of large organizations that don't change and they don't want to change. And they're very bad customers, right? Because they're like, listen, I have enough gear and enough people and enough hardware to do exactly what I want and I don't want to change it. And like that's clearly not a good fit. Where you've got these small guys say like I live or die by innovation. I want to be able to spin up a dev environment. Even though I only have 40 employees, I want to spin up a dev environment in 0 time, and it requires different network services. Those are good customers. So it's really about the speed, not the size. Yeah.
What is actually your mid-range or long-term vision? Not comparable to a feature like a snapshot or cloning.
Yeah.
So get rid of some of these legacy network devices, what has been virtualized, to find new ways for communication.
Yeah. So I mean, this is a long journey. Actually, my personal interest is to nail the data center. So like, let's say you're a traditional enterprise and you implement NSX. I want to be able to go to your data center and stand far enough away and have it look almost exactly like Google's data center. That's kind of for the data center. That's where I want to stop in the near term. But you still have whatever workloads you want. And then I actually were quite interested in moving into the WAN, or not to the WAN, into the campus, because you can provide kind of very similar NAC-based provisioning in the campus as well. After you virtualize, I think it's very interesting to change abstractions. So for example, I'm a big policy guy. Actually, I got into all of this on policy. So once you virtualize the network, you can actually build a non-stupid policy layer. So you can say things like, so today there are policy layers, but they're impossible to implement because the networks don't understand what you're talking about, and so you always do these stupid things like NAC where you're trying to implement it at the top of rack. But once you have virtual networking, I can build a full policy engine where I can say something like, it's 5 o'clock and Martin's on the computer, and therefore, make sure it goes through an IDS because I don't trust him. Or you can have these full policy engines and compilers that you compile down. And once you have that, you've actually changed operations to a higher level. So I think that after you virtualize the infrastructure, we go to the policy realm. But you have to virtualize first. I don't think people are trying to shortcut, and you never shortcut policy. You have to get the infrastructure flexible, then you can add a policy layer. And once we do this, we're no longer talking about IP addresses mean nothing. They're ephemeral, they're dynamic, they're not a good approximations for anything. They're not a good approximations for users or anything, right? So at some point, we want to get to where we're actually talking about meaningful things like users and applications. That's the goal. But we have to get the infrastructure virtualized first, so there's no shortcuts. Yeah?
Yes, just if you look at the conventional networking hardware,
Yeah.
does it need to be certified to work with NSX?
It depends. Yeah, it depends on the. If it's just providing the fabric, no. Right. I mean, so again, to go back to kind of the premise of all of this. This is the last question. Was that the? So the premises of all of this is, for the last 10 years, these big data guys have been building awesome data centers without certifying anything. And I want to provide you that model, which means you build whatever fabric you want and it'll work. If I'm integrating with a top of rack for to handle physical workloads, then we have to, because it's a more complicated problem. I've got to actually manage state on the top of rack. But if you're just using it as the backplane, like a Google or an Amazon does, I mean, they don't require certification. I don't want to require you to have certification either. Make sense? Like for any question you have on the architecture, I want to point to Facebook, and I'm gonna be like, that OpEx, that CapEx, that performance, that software innovation, I provide you that, and that procurement model. That's what I want to give you. That's my gift to you, right? Now, we're a ways away from that, but that should be your mental model for what these data centers look like, because if you have any question on performance or anything else, you look at them, and then you tell them, like, you don't know how to build a data center, and they'll correct you. Make sense? I can repeat it if you want to.
To make it more specific, Cisco is not on the list.
No, but we like 70% of our deployments are over Cisco.
Okay, so that's the question. So
Yeah, no, that's what I'm saying. So like, yeah, so I mean, they're one of our closest partners, right? I mean, we've been very close to them forever. I mean, I would say probably 70% of our deployments are in Cisco hardware. They work great, and clearly this is all supported stuff. So it depends on the level of integration, right? So for example, if I am directly integrating with a third-party X where I'm managing the forwarding table myself, then we have to require certification, but that's not required to run NSX. Yeah. Oh, sorry, this is the last question. Go ahead.
Can I tell him just to buy some dump switches, and everything I can do it on the NSX layer from VLAN access policies? So he need the switch, physical switch to connect the ports, but everything from networking perspective, he can do it on the NSX layer?
So depending on the customer requirements, yes, depending on the customer requirements. If your customer requirement is, I like F5, then you have to have an F5 there. And if the customer requirement is, I like Palo Alto Networks, you have to have a Palo Alto Networks there. But if that's not their requirement, if they're like, I just want L2 and L3 and ACLs and stateful ACLs and a basic load balancer, that can all be provided by NSX in software without requiring any of it in the network. And you can use any network fabric you want, whether Nexus is great from Cisco, and so is Dell. It's all the same to me. This is not a discussion I become a part of.
Yeah, but there is no configuration that will be done on this. It will be just a dump devices. Everything will be done on the NSX.
Exactly. There's no configuration of the devices. You built your physical network is an L3 ECMP fabric, and you never touch it again. It provides capacity, and everything else is done programmatically on the edge in NSX.
Thank you.
Yeah. Okay, guys, I think that I'm getting the thing. So thanks so much. I really appreciate you guys sticking around.